welcome to today's webcast. My name is Brian, and I will be your event specialist today. Following the presentation, we'll have a question and answer session. You can ask questions at any time during the presentation. Click the Ask a Question button, type in your question in the open area, and click Ask Question to submit. If you should need technical assistance, please type your inquiry into the tech support box on the left side of your screen and click the Send button. If you're disconnected from the webcast, you can log on again using the login instructions provided to you. If you cannot log back on with these instructions, please call support at 866-271-7592. It is now my pleasure to turn the webcast over to your speaker, Benedict Gaster. Benedict, the floor is yours.
Hi, thank you. As I was kindly introduced, my name is Benedict Gaster, and I am an architect on the programming side, the kind of software side of programming models and things at AMD. And in particular, my focus, certainly over the last 3 years since I joined AMD, has been GPU computing, particularly focused on the GPU. But as we move toward merging our cores onto, together onto a single die, which we call a fusion architecture, overall, we are starting to look at programming models for the CPU as well as the GPU and combining those and what those mean. But today, you're joining at the first of a webinar series which is focused around OpenCL. OpenCL is a low-level programming model for programming, particularly GPUs, but it's also one of the first GPU-style programming models for CPU as well. And we're going to have a number of those, and I'll give you the timetable and the program for what will be coming up in the future a bit later. But what I wanted to talk about today was, let's not dive straight into software OpenCL. OpenCL is just kind of one part of the ecosystem for parallel programming. And today I just wanted to give a little overview of what all that means for heterogeneous computing, and in particular what it means for our fusion-based architectures, both the ones that will be coming out in the very near future. Yesterday we announced Llano, which is a really kind of medium range part for kind of netbooks and everything with GPU and CPU support. It's a very nice part. And in the future we'll be announcing much more, forward-looking and different types of architectures based on that notion of the GPU and the CPU on the same piece of silicon. So, moving to the next slide. So today I'm just going to give a little bit of motivation of kind of what we're trying to do and everything, and why we think heterogeneous computing is the future and why it's important. I'm going to stop every now and then and do a little bit of terminology, but I will start at the beginning because I think there is often lots of different meanings to the same names given it, particularly in parallel. When we talk about parallel things, for example, parallelism and concurrency often come up. And what I have at my own set of definitions, I'm going to cover those. They may not be necessary the ones that everyone else has, but just so we're all on the same page, everyone knows that. And then I'm going to talk a little bit about hardware in a heterogeneous world, and particularly, obviously, because I'm from AMD, I'm going to focus on what we see that vision, and I'm sure you'll hear from other vendors and other places their vision, and sometimes there'll be overlap and sometimes there won't. And then I'm going to just talk a little bit about software in heterogeneous world and what that means, for these things. Again, I'm not going to dive down into the low levels of the programming languages today. That's going to come on in OpenCL and other parts of these webinars. Today I just want to give you an overview of kind of where AMD and particularly me see this vision going over the next few years. So I had a question, is OpenCL similar to the CUDA language and developed? Sorry, let me just check. For NVIDIA, and absolutely, OpenCL is very similar to CUDA. It's a GPU language, which means it's a data parallel language designed to efficiently run on GPUs, and they share many of the same characteristics. And we'll talk more about that as the series goes on. So, okay, so let's dive in. So, I'm sure everyone on this call, or most people, would have heard of, there's an article, very famous article by Herb Sutter in 2005 in Dr. Jobs that kind of talked about the free lunch being over. And what he meant by that was that hardware, and particularly vendors, can no longer depend on increased clock speed, execution optimization, so for example, instruction level parallelism, longer pipelines, and those sorts of things, and everything that had been going on, particularly in the 1990s, and larger caches. We just came up against a wall in the physics. And, everyone talks about this and areas of this, so I'm not going to go into details of this, but this is kind of where we're starting from. I mean, obviously we started quite a while. This was 2005. I think many of us had already realized this was the case. And the more interesting question now, kind of, the follow-on from that, what's the corollaries from that statement or theorem that he put? How is this being addressed? So the key to it is parallelism. That's it, lots of it. What I mean by parallelism, we're going to put more and more cores down, and these things can run independent things in parallel. And that's, that's the kind of crux of it. I don't think this will come to any surprise. I'm certainly not in any way stating that I've come up with this idea or anything like that. It's an idea that's been around for quite a while. But I just wanted to make sure that we're all on the same page and where we're starting from. So I think at that point, it's important then just to have a little stop on, just cover a little bit of terminology about what we mean by these things, because it's very easy to assume that everyone has the same definition that you're thinking. I often make that mistake and then realize I spent an hour explaining something to someone. And sorry, I just got a question. Okay, so I'm going to come back to the questions on OpenCL and direct compute. Someone asked a question between the difference between OpenCL and direct compute. They're going to actually be covered in much more detail in the following webinars. And so I can come back to that at the end, but I won't go into that detail now. So definition. So parallelism, it's a property of computation where portions of the calculation are independent, which means that they can be, for us, what we want to be able to do is execute those concurrently or at the same time. So, for example, here we had this little set of assignments that are happening, and A, B, C, D are purely independent of each other, so they can all be executed or run in parallel. You don't have to run them in parallel, but they can be an opportunity. So that means that hopefully we could get to calculate the result for R quicker than if we executed them in a sequential order. And I think that's an important thing about parallelism. Parallelism is about performance. It's about trying to increase the performance of an application, so the overall time taken is shortened, or in some sense, I'm not going to define what that might mean, but and so this is in contrast. Have we gone to the next slide? Yeah, so this is in contrast to concurrency, and these two things are very strongly related. Some people argue they're the same thing, but I'm not going to do that. I think concurrency is a logical programming abstraction, and in particular, what it allows you to do is build up, abstractions that can communicate between each other in a kind of way that could enable parallelism. So, for example, you could have two processes or threads running concurrently. Now, if you only had one core, you'd have to swap one thread in, run it for a little bit, and then swap the other thread back in, and so on. If you just had two threads, it doesn't inherently imply. Sorry, I'll try to do that. Is that better? Hopefully, someone's asking a question about the microphone. Now, that doesn't inherently imply that they can be parallelized or they should execute concurrently, but they could do. So it does not preclude running tasks in parallel. It's just the point is with concurrency and parallelism is that it's not a requirement for concurrency, whereas parallelism, you are indeed executing them in parallel and together at the same time, in some sense. Okay. Okay, so the last couple of definitions I wanted to get to, heterogeneous computing. What do we mean by that? And so, heterogeneous computing is a system comprised of two or more compute engines with significant structural differences. I can't get the microphone any further away. I'm sorry. Is that any better?
Yeah, it sounds good.
Okay, well, I'm getting lots of questions. People saying it's try to lower the mic boost.
Yeah, I'm working with those people right now.
Okay, great. Thank you. Okay, so as I say, a system comprised of two or more complex compute engines. And what we mean by structural differences is that, they are really quite different. For example, our GPUs today don't have the large caches that the CPUs have, and, CPUs today are designed very much for low latency accessing, and this is part of the idea of having the caches, where our GPUs are designed for, massively high throughput of memory accesses via this multi-threading architecture. So they are quite distinct in their design and implementation. They obviously have similarities. They're both computers, chips and so forth, and they execute instructions, but at some level we see them different. So that's how we see heterogeneous computing. And then Fusion, the idea is that we're going to bring two or more of these components and join them into a single unified whole. And in particular, in our case, we're going to take one of our CPUs or many of our CPUs and one or many of our GPUs, and we're going to integrate those onto a single silicon die for higher performance and low power. And there's other reasons as well, because obviously there could be cost involved of just combining one part rather than multiple parts. Okay. So, moving on to the next part of the presentation, we're going to look at what the hardware in this heterogeneous world might look like. So a question has come up: does parallelism involve effort on part of the compiler to isolate instructions that do not create hazards? We have to write and so on and execute them in pipelines first. Well, that is one type of parallelism. So that there is, loop nest parallelism, for example, that can be achieved by compilers doing things which is called approach, say, for example, called strip mining, where you might tile the loop to expose parts of the loop that can be executed independently, for example, across SSE or ABX style instructions. So that is definitely one approach to achieving parallelism and doing that. But however, personally, I'm actually a believer in explicit parallel programming models. And so, so whilst you can do it for some loops, if the program has not been designed to be parallelized, then it's very unlikely that you're going to be able to fully achieve that. And I'll come back to a little bit of that in the later few slides when we get to them. Okay, so I'm getting a lot of questions, so I'll try to move on and I'll come back to some of them towards the end. So actually the one about Fusion CPU and GPU shared memory, I'm going to get to that in just 1 second, so I'll come to that. Why do we need CPUs? Well, we'll come to that. Okay, so an AMD is a balanced platform, and one of the questions was, why do we need a CPUs? Well, I think the CPUs are very good at doing a low latency. They have very large caches. The idea is to hide low latency. So that means that you can do very small pieces of work, maybe with lots of control flow and things like that, very effectively on the CPU. And so here you can see that we could do serial workloads or task parallel workloads. Task parallel workloads. And I'll come to what task parallel is in a little bit. And of course, there is a whole wealth of existing applications out there for the CPU. And we can't just replace those. We have to be able to support the legacy. And so, if we came out with a chip that wasn't capable of running Windows and its legacy applications, then we would be a bit stuck, getting forward. I think one of the reasons that GPU computing has been successful, particularly if you think about NVIDIA and their promotion of CUDA and things, then is because there was already a large market out there which they could tap into, and they weren't trying to bring out something completely new. I hope the post will be recorded. I'm sure it will be. So GPU, on the other hand, is an ideal place for parallel processing. And in particular, it's very, very good at running data parallel processes today. And one of the big problems with the today's models of GPUs and CPUs is that the CPU is quite a long way, in quotes, from the GPU, and it has to go via the PCIe bus. There are different memories, so things have to be managed, and there's costs of managing those things, which if you have them on the same die and they're sharing the same memory, which absolutely Fusion parts for the CPU and the GPU will have a shared memory. There will be a single unified memory, and then we can reduce the cost of both producing them financially, but also the overall performance for a wide range of configurations. And I'll give you an idea. The reality is today, that the single core era, the kind of Herb Sutter thing where he said that was stopping to scale, it was certainly enabled Moore's law and other things, and microarchitecture challenges and enhancements such as instruction level parallelism helped to keep that going. The problem was we came up with that the power just became too much. We couldn't build the chips within a reasonable power envelope, and the complexity of these things. Some of the microarchitectures that are under x86 or ARM and other chips like that are very, very complex and become very difficult to build and very challenging. Verification, often the teams of verification are much larger than the engineering teams, and so on. So then we slowly moved into the multi-core era. And again, this continued with Moore's law. We started to reach for desired throughput, and we had a lot of experience with SMP-style architectures, and software started to develop. The problem came then was that again we were constrained by power. We still had some limitations on software availability, and the biggest issue I probably would say is the scalability. The problem is that if you want to have coherent caches with 4 processors or even 8 processors all communicating, that was one thing. But if you then wanted to have a coherent cache where you had 64, processors communicating, that became a pretty difficult thing to build and had real issues with scalability. And so, as we see it, we're starting to move into the heterogeneous era, and we're just really right at the bottom of this. You can see this at the little bullet point at the bottom. Again, Moore's law is enabled by this. There's lots of abundant data parallelism, and GPUs are very power efficient. There's lots of replication of units, and they're not clocked nearly as high as something like the x86, which runs at 3 or 4 gigahertz, whereas the GPUs are running probably a gigahertz or less. And the biggest issue today, probably with the heterogeneous systems, is the programming models. They're quite limited today. OpenCL is excellent. I think it's a great starting point, but it's certainly not the finishing line. And there are lots of the kind of things we'd like to be able to do on the CPU side of programming models, and maybe move some of those to the GPU programming model too. The other thing, of course, is communication overheads. I talked about the PCIe being a bottleneck, and we need to start addressing those. And of course, Fusion does start to do just that. But I think I really want to make clear the whole point about this slide is that we are really right at the start of this era. It is a new era that seems to be emerging, and not just us. Intel have their Sandy Bridge parts, and I'm sure ARM and others will be developing heterogeneous systems in this way that's really going to move into a new era of computers. So, and you can see why on this next slide why the GPU is important. I think that this is the key thing. You can see these lines here. You can see the gigaflops of single precision performance going on and on. For us, with our latest GPU, actually our last generation of GPUs, 5870, that's up over 2 teraflops of single precision performance. And we continue to improve that over time. And at the bottom here, you can see the CPU. So now this is not a criticism on the CPU. It's just an observation that, the data parallel design of the GPU, it's very easy to kind of keep scaling that up and adding, ALU units to get more single precision performance. Now, of course, the drawback with that is that the wider and wider these things come, the more things you need to be able to find to execute at the same time. If some of those are hidden within a bit of control flow and things like that, then you don't necessarily always get to this peak performance. And I really think that it's the combination of the CPU kind of style workloads drawn in to a GPU execution of very wide data parallel tasks that will really bring out the best of an application. So we can see double precision continues at a slightly lower rate, but it's still is still pretty high. So here we're just under 600 gigaflops. And the NVIDIA have a similar number here for us, and you can see that double precision, which is important for many applications, continues to improve over time. And here you can start to see. The nice thing about double precision is that if we do it against watts, you can see that the amount of power for the same, for the much bigger performance across here for the GPU, for example. We're not as low as the CPU, but then we're over, nearly 600 times as much flops, for example, or double precision flops. And you can see the bandwidth trends here. We can see that discrete memory is continuing to bandwidth is. So this is on a discrete GPU device where it has its own DDR5 memory, and you can start to see that the memory bandwidths are still going up, but they're not increasing hugely. There is a difference between the number of flops that we're adding and the memory width and the memory bandwidth that is increasing. But you can still see this is a considerably high bandwidth, at 150 gigabits per second compared to the CPU, which is probably around 40 gigabits per second on high-end CPUs as well. And of course, unfortunately, the external bus gigabyte does not increase. So that is one of the bigger issues that we face in the future. Again, you can see the trends with when we start considering, gigaflops per watt or gigaflops per square millimeter. The GPU has a real kind of influence here and continues to improve over generations. Okay, so I really think that there is a need for a CPU. Some people ask why can everything not be done on a GPU? And I just think that if we try to do all the workloads that you can do on a CPU today on a GPU, those slides I just showed you for power, for gigaflops and those sorts of things won't look the same, because we'd have to sacrifice some of the performance on those on the GPU device to add much larger caches, say, for example, to start being able to handle much more complex control flow. And I'm not saying that at all the GPUs won't start to have some of those features, because of course they will, particularly once we start putting them onto the same silicon, which this slide is showing you. It's showing you that, one area we're moving from, the unacceptable program accessibility of kind of GPU computing into mainstream computing. And here we're bringing the drivers up on the red line, all of that, to make it more of a unified programming model. And I think that is, bringing the two together is kind of really where you'll get the key benefits. Don't necessarily add everything the CPU can do to the GPU, and equally don't make the CPU into a giant GPU, with latency, because then we get the best of both worlds without necessarily sacrificing those things from one another. Okay. Someone asked, do you consider FPGAs or other hardware accelerators? So I'm not going to talk about those directly in these things, but of course they could well make up a heterogeneous system. That an FPGA is quite different from a GPU, at least in some sense, and how they're programmed is quite different. And so I think they are an interesting area of development and research. How they will appear in future systems is unclear to me. And I'm sure people who are more expert in FPGAs would have maybe more to say about that. I certainly hope so. Okay, so why AMD Fusion APUs? And I think this is coming back to what I said before. This is a balanced approach. x86 CPU owns the software universe. So this is really another key reason why we can't just drop the CPUs. We could add the GPUs, make them handle all this stuff, but that would be a lot of silicon and would probably increase the power and the benefits that we get from GPUs today. So we still need to be able to support, the Windows, the Linuxes, the many thousands of applications. Some people, I'm sure, still run applications that were written in the 80s, and so forth. And I think on a more technical level of kind of, we need to be able to handle very branchy scalar code still. It's not likely that all applications will suddenly emerge as a parallel application. The one thing I don't actually think that would be sensible, because you only need to accelerate the hotspots in your program to get a good performance improvement. And some things just don't easily express well as a parallel computation. For example, if you want to do a print statement followed by another print statement, they are inherently sequential in execution. So there's always a time for kind of ordering in that way, I think. So I'll try and answer a couple of questions before moving on. And let me just get to the other side. So here, the GPU is the game changer. I kind of think that there's certainly I'm not really proposing that the GPU is the best thing in sliced bread and is solving all the problems. It's just it adds a level of parallelism and throughput that the CPU does not have today. So adding them together, all of a sudden, you get this kind of really kind of significant future, and it becomes much more programmable, at least potentially much more programmable. That we've increased the flops considerably without actually ramming up the amount of power we're consuming. And you could argue that we're now providing with the best of both worlds. That's kind of obviously I put that with a pinch of salt because nothing comes completely for free. So is the idea behind Fusion related to systems in the chips in any way? Absolutely. Fusion is an SoC, so it is a system on a chip. It is very closely coupled with that idea, that we are bringing, multiple types of devices into a single chip and integrating them together. And okay, so I'm just going to try and answer a few questions. I can't promise to answer all of them at this time. So that's one of my favorite topics. Do you expect pure functional programming languages, Haskell, ML, etc., to be key to enabling heterogeneous computing? Now, that's an interesting question. I don't completely see that. I think that those languages have already massively influenced existing languages. For example, I see much of that is in C# has come from the functional programming world. For example, they call it delegates, and Haskell call it lambda functions, and C#, and C, of course, C++ is going to have lambdas. And so absolutely, do I think that Haskell is going to become mainstream programming language? I don't know, probably not. No. Do I think that elements of it will make it into other languages? Absolutely. And those languages will become mainstream, definitely. And that's true of ML and all those other languages as well. Okay, I'll answer one more question and then move on. What will happen if you use GPU to handle CPU's tasks? Also, how do we know a task can be parallelized? Well, that last one is pretty tricky, and I can't cover that in details today. Do I think so? I think today, if you use GPUs to handle CPU tasks, you'll be running at a very low efficiency. So, for example, we're a 64 wide vector machine on our GPUs today. If you're running a single scalar thread, then you're just running one of those. So you're losing 1/64th of the GPU, and that's not to mention that we have 20 of those units replicated across. So I think that's a big issue. The other issue is, of course, that we can't handle all of the CPU tasks. For example, we don't have preemption on the GPU and things like that. So there are some things that we don't today support. I'm not saying we'll never support those, because I think we probably will, but today we don't support those. Okay, I'm going to move on because I haven't got that long. Okay, so this will give you an idea of what the first generation of our Fusion devices will look like, and not this slide, but the next slide will. So today, this is what our PC looks like with a discrete GPU. You have the CPU, many core CPU. Via the North Bridge, it talks to the discrete GPU via the PCIe. The discrete GPU has its own graphics memory, and the CPU has its own system memory. These memories are completely distinct. They have no relationship other than they're on the same, machine. They are no way synchronized together. The only way to move data through and forward is to use explicit memory transfer operations, DMAs or whatever. And then we move to the Fusion APU Based PC. So this, I want to be clear about this. Whilst I can't talk about our later Fusion GPUs, this is really a first step to where we're going. So, for example, you'll still see this kind of North Bridge bus kind of in here. I'm not going to talk about quite what happens to that, but you can imagine what could happen to it, I think. The key thing here is that the Fusion GPU is moved inside the single die. This little green faded box is a single piece of silicon, and they're talking directly together. So all of a sudden, we've massively increased the amount of memory bandwidth between the CPU and the GPU together, where we don't no longer have to communicate via the PCIe. Of course, we can still have discrete GPUs attached to this, but that's not the goal. And again, you can see that attached to this green box is the system memory. So now the Fusion GPU and the CPU are sharing the same system memory. And again, so we're starting to merge those together. And yes, it is true that it's 12 gigabytes both ways, but it's often the case that you can't run both those channels dually because of the way the GPU will be worked up. It means that you'll have to be reading and writing, so you'll have to double buffer things. So it's not to say that's not completely doable. I completely agree that that is doable, but again, that's putting another layer of complexity onto the programming model and the programs that are done. So someone has asked the latency of Fusion versus PCIe latency. So the latency of a Fusion part is, I don't know, I can't remember the exact numbers, but it's much, much lower than it is on PCIe latency. And of course, we don't have the setup. There's a lot of other things that you can factor into here. Here I've just given the kind of broad numbers for the actual feasible peak performance that you could get. But I think that the important thing to think about with the Fusion GPUs is that in the end, they're really enabling a much simpler programming model. It's absolutely not necessarily giving everything away and getting that maximum performance. But again, you're getting pretty near close peak performance whilst being able to simplify the programming model. For example, in the future, you could imagine that you might be able to just dereference an x86 pointer on the GPU. So all of a sudden, you can just pass around your data structures and everything, and there's no way that's going to happen easily on the discrete GPU. Yeah, so someone's asked, you have 150 gigabytes only on 20 gigabytes for actual memory bandwidth. So 150 on the discrete parts and 20 gigabytes for actual memory bandwidth on the Fusion APUs. And that's absolutely the case for this particular Fusion APU that I'm showing you. So this is a middle to low end part that I'm showing you. I can't talk about the high end parts, but hopefully you can extrapolate from that between those two numbers and start to think about how they might relate and where we might be getting to with a Fusion GPU, a high-end Fusion GPU. We just haven't announced that yet, and today I can't talk about those things. Okay, so I'm going to move on because I do have quite a lot of slides and not that long. So unparalleled processing capabilities in mobile form factor. With shared memory for CPU and a GPU, it eliminates a number of copies. So even though we've reduced the amount of memory bandwidth on these smaller parts compared to the discrete parts, you can actually think that in reality, a lot of the bottlenecks were not necessarily throughput on the GPU itself, but transfers between the CPU and the GPU and going back. And so we've kind of improved the performance there, even on the lower end parts. They get a performance benefit. And of course, we've enabled architectural innovations, between the GPU and the CPU. That, a lot of that's still going on. We haven't made any of that public yet. These parts are just the first step in that. And the key thing is that we're starting to build a scalable architecture that can be a broad range of platforms, from mobile to the data center. And really, these first APUs are just this kind of, we're touching the very tiniest bit of the iceberg that it's going to become. And again. Okay, so I'll answer one more question before moving on. Previously, you made the point that GPU memory bandwidth has been increasing to keep pace with the gigaflops. How is this overcome in the Fusion GPU? Or is that not important? It is absolutely important. And, okay, so I'll answer this question, then I've got to hold on. Okay. So the reason being is that, this is, it is very important, and the first generation of the APUs probably don't resolve this problem completely. They resolve the problem of the PCIe bandwidth and increase that. But what they don't do is, and the latency in particular, but what they don't do is they don't necessarily completely resolve the gigaflops per memory bandwidth. However, the GPU itself is a much smaller part, and so it doesn't have quite the number of the gigaflops that I showed you of the high-end parts originally. So the trade-off is actually smaller, and so it's not that it's not important. It's actually the impact is not quite as much. But anyway, I do need to move on, so I'll get back to questions at the end. So I think the key question is that heterogeneous systems are being built, and there is no question that they will be built more and more of them. The question becomes is that how do we program them? We know there's enough workloads to utilize these things, but we just, programming 10 cores is complicated enough, but what happens if we have to program 1,000 cores, maybe even more than 1,000? I really believe that the future of performance is entirely about software. It's entirely about how we're going to program these things. And there's a couple of slides here that talk about where you can find out more about this stuff, and one of them is at the Fusion Development Summit, which we've just announced and will be in June the 13th to the 16th in 2011. You can find more about that online. And the OpenCL webinar series itself is designed to help you advance your experience in parallel programming, but particularly focused today on OpenCL. I expect over time we'll have more webinar series which will be more targeted at CPU and GPU programming. And again, you can find more information about this webinar series online. So, getting to the final section of the talk was software in a heterogeneous world. What lies ahead? So, from a talk that Guy Steele gave in 2009. Guy Steele is from the Java community and Scheme and other places. But in particular, he says the future is parallel. What's a programmer going to do? And so I think this is the million-dollar question, and it does have many, many different answers. Here's just some of them. I can go on and on and on and on and on and on. And we keep going and going. And these are just some of my favorite languages. By no means they're all of the things that are out there today. So all of the green ones are kind of, you could argue that they are parallel programming models. POSIX and Win32 are very kind of coarse-grained thread APIs, while something like concurrent ML is all about abstraction, not necessarily running things in parallel. And then Microsoft's Task Parallel library is about breaking things down into nice tasks of work, which could be offloaded to different cores for execution. And these kind of bring me to my two orange boxes, where I want to talk a little bit about task parallelism and data parallelism. And so these aren't programming languages; they're more about methodologies, and the kind of, I think, are the key to any success. So in an application, I've just taken what I consider to be a kind of coarse look at a first-person shoot 'em up. And you can see that there are many different types of parallelism in such an application. Here we have the AI, which very much task-style parallelism. We have these two things doing physics systems and particle systems in the middle, which are very much data-independent, data-parallel systems. And so on. We can have things for user interfaces, maybe some cloud stuff via the network. So, a term that comes from Aaron Lafona, Intel, is this notion of braided parallelism. Most applications that we're going to want to accelerate in the future are a kind of decomposition of task and data decompositions. And you could see this from this application. And so task decomposition, the idea is that we divide the problem by type of task to be done. For example, in a game, we can have many tasks and jobs. Some may be fine-grained, i.e. very short-running. Others might be long-running and very data-parallel, for example, as we saw for the particle systems. And so if you're building or using a programming language, a model based on tasking, you need to be able to have dependencies between tasks, i.e. run one task, get the result, and pass it on to another task. You need to possibly communicate between tasks. You're probably going to want to make sure that if one core or one part of the system is not doing something, then let's give it some work and get that busying. That's often called load balancing, and so on and so on. These are kind of the major factors that you'll find in any kind of task-based runtime. And most of these systems are based on a notion of load balancing, which comes from some seminal work in the 1990s by people at MIT on a language called Silk. And the idea here is that, you're going to want to have, these are your cores, the little boxes, the sad faces are core, and the green faces are happy because they've got lots of work, which are these blue boxes. And of course, the idea is that, you're going to distribute some work. It's generally done by this kind of work stealing. So 4 has stolen some work from the others. So I think this will come up time and time again in task-based and programming models, and probably is what will happen. I need to move on. There are lots of examples. Most of them today are all for the CPU. So there's Intel's set building blocks, Apple's Grand Central Dispatch. OpenMP has a tasking, OpenMP3. I'm not a fond of tacking on parallelism. It comes back to my belief that programs need to be explicitly parallelized using constructs that are part of the language. That's not to say you shouldn't use OpenMP. I'm just saying that I'm not a big fan of it. And then from the managed language perspective, I think the most prominent one to date is the Microsoft's recent .NET 4 runtime, which supports this task parallel library for all of its languages, C# or F# and so on. One of the big things today, there are choices about whether you have a different OS. So, for example, if you're using Apple, then the Grand Central Dispatch might be the right choice, and there are different options there to move. So I'm going to move quickly on. Although it's not. Okay, so data decomposition. So this differs from task decomposition. Is the idea is that you have many elements and they are independent and they're going to be worked on together in parallel. So we talked about that in a modern game. This could be a particle system, thousands, maybe hundreds of thousands, even millions of independent, little sparks in a fireworks system that are just independently reacting to forces and so forth applied to them. Obviously, you might want to be able to group some of those together, and so in a real implementation of data parallel execution might account for some local communication. So, for example, you might have a little cluster of particles flying around the system which are communicating with each other. You're going to need to be able to synchronize those kind of communications and so on. So they share a lot in common with task parallel systems, except that they are really executing independent pieces of work. There are popular languages, and so today we'll get to the unmanaged kind of C, C++ style stuff. Then I think the two most prominent ones today for these are probably Khronos' Open Compute language, i.e. OpenCL, which we're going to talk about in the future in future seminars. And you can notice that this is probably the only one that really has CPU and GPU, at least in the unmanaged support. There's NVIDIA's CUDA, which is obviously for GPUs only. And then there's OpenMP, certainly has a lot of data parallel, is written and designed for data parallelism. Again, that's CPU only. Managed languages, we're starting to see different things emerge. So Microsoft Accelerator, I think, is an interesting thing for .NET 4. There, they do support both the CPU and the GPU. And more recently, AMD's Parallel API for Java, which is basically a high-level API within Java that can target OpenCL, CPU, and GPU. Again, you're running into different OS and different options. Okay, so let's move on. Okay, so I think that in the end that it's going to be a combination of these two things that become the emerging programming model of the future. It's not just going to be one. I think that this is a job graph on the right-hand side. It's supposed to be very small. It's a very large job graph from a single scene in DICE's Battlefield Bad Company 2. And you can see, if you can see here, there's little ones that are all running alongside at the bottom here next to each other horizontally. Then they are all data parallel operations, whilst all the little lines, the edges in the graph, are describing task dependencies between one another. And you can see up here there are more data parallel executions. So really, I think that the future is a combination of these two things. And again, it's not a coin that I termed, but braided parallelism seems to be a nice term for this. So again, we can put this all back together. So I'm again bringing through the slide that we talked about in the hardware section of things. You can see the AMD's Fusion APU. How are we going to lift this stuff to the mainstream? To make this a programming model that not just experts can use. I mean, OpenCL is not too difficult, but I think that it's probably not. It's going to be a little bit of a shock if you're a Java programmer or if you're a C# programmer, for example. And why would you want to step outside of those languages if that's where your day job is? I'm not saying you should never do those things, but if we want to bring parallelism to the mainstream, I think that we need to merge these models. And that kind of brings me, I think braided parallelism is a natural programming model for heterogeneous computing. And so combining things like OpenCL with PBB are kind of strong ways of moving that forward and making a strong approach in the future. So I'm sorry, I rushed those last few slides a little bit, but I have just made it in time, and I'm now going to take some questions and answer questions. So there are a lot of questions. I'll kind of just work up from the bottom for that. So can I just ask the operator, can everyone see the questions when I select them, or do I need to read them out?
No, you need to read them aloud.
Okay. Okay, so this is a long question. So OpenCL is driven by GPUs. How does that programming model fit to the CPUs? Does it make sense to use OpenCL for programming CPUs? Or in other words, as a software developer, I would prefer a programming language in which I can describe solutions to my problems and a kind of enhanced compiler that maps my solution to heterogeneous hardware. So that's that's a quite complicated answer, I think, to this. Absolutely, I think that OpenCL can be used to program CPUs. Now, the question comes, do I believe that the same OpenCL kernel, which is the unit of function that gets executed on either the CPU or the GPU devices, can be written easily for the CPU or the GPU? And no, I don't think that's possible today. Today, you have source language portability, but you don't have performance portability. The problem is that for the GPU, for example, it makes sense for me to have reasonably large number of threads, or what OpenCL calls work items, running in parallel on a single compute unit. On the CPU, you're really just having one, thread, I'm going to call it, or work item, as OpenCL calls them, running on a particular core is more effective. That, of course, will then influence the way that you design your program and your algorithm. And so today, I don't think OpenCL provides the answers to that. I think that future generations of OpenCL are being developed that will provide features that make that much more easier for portability. For example, container types. So, for example, something like a vector type from the C++ standard STL, that would be useful, because if you had routines that could then underneath be compiled using a special compiler to either the GPU or the CPU, that would hide away some of those idiosyncrasies from the developer. So I do think that enhanced compilers that will map solutions to different parts of the systems will play a part. Okay, so I know a lot of people have asked, will this presentation be available for downloading? And I've had to try a few of those. Absolutely, the presentation will be available for download. I'm not quite sure when it will go up, but I'm sure it will go up in the next few days, and it'll be freely available on our website. Okay, so this is a good tool. This is a good question. What about debugging tools? It is one thing to compile an algorithm, but without a way to trace through GPU code like PIX for x360 on Windows, all you end up with is buggy programs and the wrong answer and no way to figure out why. So I completely agree. I think that debugging on the GPU has taken a while. I think that NVIDIA have made some very good progress with some of their tools, and we are AMD is about to in the next few months we'll have a very similar solution. I'm not saying the same solution, but we'll be able to provide similar functionality where you can do full step debugging, you can do breakpoints, you can do watch points, those sorts of things. So that will be available on the GPU as well from us too. And of course they'll be integrated at least into some of your favorite IDEs and so forth. So I think that will become easier over time. Now, that is not to say that we're going to be able to provide a debugger where you can debug a single lane or a single work item or thread in OpenCL or DX Compute, for example. What I won't be able to do is, we're not going to be able to provide you with be able to resolve every program. If you have a deadlock, for example, or a live lock, these problems, debugging parallel programs are still complicated and introduce new difficulties in the world of debugging. Okay, so next question. You used a Battlefield Bad Company 2 as an example of something that can benefit from GPU. Can we expect a future where enthusiastic level systems will have the GPU core on the APU will handle 100% GPU tasks, while a discrete GPU will continue to handle graphics. I think that's quite feasible. I mean, I can't predict exactly what will go into different things, but I certainly could imagine that if you were an enthusiast level system, you may well have a discrete GPU, and you may well have an APU in your machine as well, even maybe two APUs. And so the distribution of how that will be divided up between graphics or GPU, I think will probably depend on the runtime at that date, and also user configuration. But yes, absolutely, I can imagine systems existing like that. So I got the question, can I use OpenCL for CUDA-based GPU? Absolutely. So NVIDIA supports OpenCL, and it runs on all of their the same family, the same set of families that the CUDA run on. So I'm not saying it's all of their GPUs, but certainly anything you can run CUDA on, I think, will run OpenCL. I mean, obviously, you need to check the details with them, but yeah. Okay, I'll try and slide up a little. I have a lot of slides, so I'm going from the bottom, but that seems a bit unfair. Okay, so how different is the Fusion GPU from the discrete GPU? So that would it doesn't. The GPUs are actually very, very similar. They have some slight differences because of the processor they're on and silicon design, for example. But what it really comes down to is that a particular Fusion CPU system will have a particular, depending on what market it's designed at. So, for example, the one I showed you, we talked about the Llano. Llano is a kind of middle to low end part aimed at low power netbooks and so forth. Then that will not have the highest, the biggest, the super duper GPU on it, but just because of the power constraints wouldn't fit, and the market is not there. Whereas if it was a very high end Fusion part, targeted say at servers or enthusiast machines, then you can expect that to have a much stronger and GPU on it. So we will have a whole range of these Fusion parts over time, and to challenge all markets, I suppose. So look at the question of OpenCL extension for shared memory, CPU and GPU. So we do indeed have an OpenCL extension for this. I mean, it's basically, at the moment, is based around the idea that it still fits into the OpenCL programming model in the sense that you still deal with buffers and things, but we have a way of saying these are shared between the CPU and the GPU, so you get basically zero copies, as we and some other vendors like to call them. Now, that's not to say that the OpenCL model today is that you can take an x86 pointer and dereference that on the GPU, on the discrete GPU. I'm sorry, on a Fusion GPU. And the reason being is because we're not today going to be mapping all of the x86 virtual page tables and so forth. Again, I said not today, so I'm sure you can extrapolate what that might be in the future. But that's where the model is today. Okay, let me have a look. Okay, sorry. Okay, when do you see OpenCL being used in the mobile space? What OS or programming languages would be best fit for the emergence? Not quite sure I quite understand that, but I mean, obviously, I can't talk about at Kronos. There are a number of embedded mobile people involved in the development of OpenCL. So I think you could read from that there definitely is going to be OpenCL implementations for the mobile space. All of the main vendors are there. All of the main people, ARM, Apple, who have these embedded devices, Nokia, Qualcomm design embedded chip. They're all there, and I believe that they will be releasing OpenCL implementations for that space. I really think I can't say much more about that because it's not, well, one, I don't necessarily know exactly when those things are going to come out, but also it kind of would be the Kronos thing is under confidentiality, so I can't share that generally. Okay, so here's another question. How does Fusion compare to Intel's Sandy Bridge? So I think the two are very related. They're strongly, and I think that's what I was trying to hint at the beginning of the talk. it's not just AMD that believes that heterogeneous systems of the Fusion or Sandy Bridge style are the future. I think that we're seeing it with Sandy Bridge. I think the industry in general has been looking at SoC designs, particularly in the embedded space, for 15, 20 years now, at least. And that seems to be the general consensus of where we're going. So I think they definitely compare very similar to that. Now, of course, the actual chips themselves have different benefits. I think that and I don't want to get into a marketing thing and something, but personally, it looks like AMD's GPUs are much stronger than Intel's GPUs today on the Sandy Bridge. And then you could argue that maybe the x86 cores of the Sandy Bridge are pretty strong as well. So I think there is kind of trade-offs and benefits. I think that the more technical details and comparisons would need to be done by our marketing department. And that's not what I'm involved in. But I think they are quite similar in many ways. And they certainly would, in the future, as both of these things develop, I would expect that the programming models for these will be similar as well. So there's a remark that CUDA has CPU support now. It's certainly been, it was certainly announced at the recent NVIDIA conference. I don't think you can actually get it yet. And absolutely. I mean, I think that's true. I mean, I think that if you want to run a CUDA-style application on the CPU, then that would be a good choice. I think there are benefits from OpenCL. I think is that it's cross-vendor, all the obvious things that I would say, and I think that CUDA is going in a slightly different path to OpenCL, and that's not to say one is better than the other. I think that they're just different choices and different decisions, And for me, I think the interesting side of braided parallelism, those sorts of things, that's where I see OpenCL going. And whether CUDA will do that, I honestly don't know. I mean, I don't work at that company, so I can't say. And it'll be interesting to see how good the CPU support is. So so there was another question about the same thing. So there was a question about, in your opinion, which languages offer the best braided parallel? Well, that's an interesting question. I don't really have the complete answer for that today. I think that in the managed space, which I've been looking at quite a bit recently, I think that something like C# actually has, with it has a very nice level abstraction where you can program both in task-based parallelism, and they have like these for each constructs, and you can do like reductions across groups of tasks, which are basically data parallel tasks. Of course, that's not being accelerated today on the GPU. I mean, hopefully in the future that will be the case. And so something like that, I think that Intel's thread building blocks for a CPU certainly has both of those models, has some nice data parallel constructs, parallel for constructs, say, for example, and then also is a very nice task parallel based model. And again, I can envisage that, something like TB or some derivative of it, TBB, moving, to support scheduling onto the GPU as well as time goes by. Okay. How much longer do I have?
You're currently at the top of the hour.
Okay. So I'll answer one more question then, shall I? So are there any applications that are waiting to take advantage of this capacity in the near future? So absolutely. I think that, data mining is an obvious application. And I'm not just kind of thinking of, the kind of on the data centers, of the Google-style data centers. Data mining in something like, searching for someone's face in an image in Facebook is hugely popular, for example. And I know that there are applications that are emerging from some of our partners that will address that. I think that's an obvious one. Image processing, image search is an obviously data parallel operation. I think that there are games, definitely the acceleration of games around some of the other systems, so accelerating AI, accelerating some of the physics-based systems. In that is something that we've been looking closely at. And then I think the more traditional data mining, so from a k-means perspective, that accelerates very well. So there I think these are all of good applications. There are obviously the obvious HPC kind of supercomputing style applications, which would always benefit from accelerating things like matrix multiply, and less interesting, but obviously very require a lot of flops. And those kind of operations are already being accelerated by these kind of systems.
And do you have any closing remarks?
So I kind of think that does actually close quite well. Is that I believe that I think that the emergence of these heterogeneous systems, whether it be AMD's Fusions or Intel's Sandy Bridge style architecture, is really is moving us into a new era. And I don't believe yet that anyone really has a complete answer to the programming model question. I think that I wanted to show you through this slide that it's clear that AMD are very strongly thinking about this, and we believe will be a leading contributor to that going forward. And I think it's clear that companies like Intel have also already been, TBB is an excellent product and is leading the way forward in that as well. And I think we can expect these things to become, together over time.
Great, thank you, Benedict, and thank you everyone for joining us today. This concludes our program, and you may now disconnect.